Okay, so good morning once more. This morning we begin with a lab on GRE, generic routing encapsulation, a protocol whose main purpose is to share dynamic routes over the public network, over the internet. So this particular protocol will enable us to share the routes within our private network to the branch, and vice versa. Okay, I think someone's mic is on. Godfrey. Okay, I've just muted you. Okay, so let's look at this. This lab is actually a continuation from lab 3-4 on VPNs. The problem with VPNs is that a VPN. Hey, Godfrey. So we have three formats. So supporting dynamic routing with GRE. So the learning objectives to configure an ACL to support GRE encapsulation. So the problem with VPNs is that with a VPN, you cannot be able to share dynamic routes over the disparate locations, like between the headquarters and the branch over the internet. So with a VPN, you can't do that. So if you really want to share those internal routes, you have to use GRE. So the objectives to establishment of a tunnel interface for GRE and also implementation of what you call the GRE keepalive feature that is used to ensure that the tunnel is up to avoid having what we call a black hole. Want to change my Wi-Fi to a more reliable one. Just a moment. Okay. So the topology is what we already did on yesterday's lab. So I've already implemented this on my ENSP. As you can see, the scenario still remains R1 is at the HQ, the branch is on a different town, for example, and they have been connected over the internet. So remember yesterday we were creating a VPN between R1 and R3. So today we want to enable GRE so that they can be able to share their networks. So let's see here. Is there anything else we need to do? I think we have a loopback. We have a loopback that is supposed to be on R2, which I have not configured. So I will include that. So on R2, we are supposed to have a loopback 0. So loopback 0, 10.0.2.2/24. So we're going to configure this loopback on R2. So I've already done all the other configurations. So let me just create the loopback here on R2. So interface loopback 0. Okay. Then IP address 10.0.2.2.24. Okay. I'm not sure whether we are supposed to advertise this on OSPF. this particular network on OSPF. Let's just follow the instructions and see, because I haven't gone through the lab. So the scenario, a requirement has been made to allow networks from other offices to be advertised to the headquarters. So following the implementation of an IP security VPN solution, it was discovered that this was not possible. So after some consultation, the administrator has been advised to implement a GRE solution over the existing IP security network to enable the enterprise offices to truly operate as a single administrative domain. So to enable R3 to be able to share its internal routes to R1, to the headquarters. Okay, so note this is a prerequisite of lab 3.4. So 3.4 has to be completed before doing this lab. So that's exactly what I've done. So on step number one, we are supposed to set GRE traffic as the interesting traffic. So we're supposed to create an ACL on R1 with this particular rule. But there's something I wanted to confirm on OSPF. Is R2 advertising that network? Okay, so R2. Okay, I think it's supposed to, but we'll get to that. Let me just advertise it, because I think it's what is supposed to be done. So OSPF1 area 0, we advertise that network 10.0.2.0.255. So actually I can just check display this. Okay, so we're also advertising 2.0, the loopback on R2. Okay, so let's go ahead and now implement the ACL. So we are supposed to create an access control list on R1. So ACL, we already have ACL 3001. So this time we want to do R5, rule 5, sorry, permit GRE source. So 10.0.12.1. Then we can use 0.0.0 or just that, with a destination of, if it's going to 23.3, we can just use 0 instead of 0.0.0. So can do that. Then we also do the same for R3. From R3 to the headquarters, we want to allow packets that are heading to the headquarters. So we create ACL 3001, rule 5, permit GRE source. So if it's coming from our internal network and the destination is our headquarters, then we want this ACL. This is supposed to be the one, sorry. We want it to be permitted. So that's what we are doing on step 1 on the headquarter router and the branch router. So let's go on and proceed to step 2. So on step 2 now we're supposed to create a tunnel interface. So create a tunnel interface and specify GRE as the encapsulation type. Then set the tunnel source address or source interface, and also set the tunnel destination address. So that's what we're doing here. So on R1, we create the interface by doing interface, tunnel, then the number of that particular tunnel. So we want to create 001. Then we specify the source address of this particular tunnel. So we specify, we give it an IP address. which is a public IP address. So 100.1.1/24, like that. Then we specify the tunnel protocol. So tunnel protocol as GRE. Let's just do a question mark. So we can have IP security, we can have GRE, IPv4 to IPv6, IPv6 to IPv4, MPLS, or none. So we've looked at IPsec and now we are doing GRE. The other ones, if you do HCIP, you're going to learn about them. So we want to specify the tunnel type as GRE. Okay, so once you're done with that, we are supposed to use the source command to specify the source address. So the source address is actually the physical address that is the egress interface that is connecting us to the internet. So really, the source address is this physical interface, gigabit Ethernet 0/0/1 on the headquarters. Because right now we are on R1. And the destination address is this particular address on the branch, the ingress interface on R3 on the branch router there. So we do that. So we do source. We can either do the interface number or the IP address. So right now we are using the IP address. So 0.12.1. Then we also do destination. So we also do destination. So 10.0.23.3, which is the interface on R3. Okay. So after that, we can go ahead and do the same on R3. So on R3, we also create a tunnel 0/0/1. We give it an IP address, a public IP address, so 10.0.1.1.2. So that is the address we give it, /24. Then after that, we do the tunnel protocol as GRE. Then after that, we can do the source. So this time the source address is 0.23.3, and we also do the destination, which is supposed to be .1.2.1. So we can see once we configure on both ends, then the status of the tunnel will turn to up. Okay, so let's go to the next step, which is configuring a second OSPF process to route the tunnel. So you remember, we already had OSPF1, so we also want to create OSPF2. So add the tunnel interface network to OSPF1 process and create a second OSPF instance of the link state database. So OSPF2 for this particular network that is interconnecting router 1 to the internet and router 3 to the internet. So be sure to remove these networks from OSPF1. So we are supposed to remove this network and this network from OSPF1, then also advertise the 100 network that we have specified as the IP address of the tunnel. So in this particular step, that is exactly what we are supposed to do on R1 and R2. On R1 and R2. Okay, so let's do exactly that. So let's begin with R1. Okay, so on R1, we go into OSPF1. area 0, we can do display this. So the first thing we want to do before we advertise, we want to undo network 10.0.12.0. We no longer want to advertise that network. So we undo it by using the undo command. So if now we do display this, we only have two networks. So we no longer have the 12.0 because we're going to advertise that using another OSPF process. And the next thing we do is to advertise the 100 network. So network 100.1.1.0, and the wildcard mask is that one. So we advertise that particular network in process 1. So after that, we can quit, then create OSPF 2. So 2 is for the process number there. Router ID, can just give it a router ID of 1.1.1. Then area 0. Then now here we can advertise the network that we've deleted from process 1. So here we can advertise 10.0.12.0. Then we go ahead and use the wildcard mask there. So now we are good. Hope we have advertised the correct thing. So this is correct. So we go to the branch router and also perform the same. So let me quit from the tunnel. If I do OSPF, it goes directly into OSPF 1. So area 0. Then here we can do display this. So we want to get rid of this network. We no longer want to advertise this network in process 1. So we do undo network 10.0.23.0.255. So should go now. Good. Then we advertise the network 100.0, 100.1, I'm sorry, 100.1.1.0.0.255. So display this. So we are now advertising this network on R3. Okay, so let's go ahead and create a second OSPF process. So OSPF2, router ID, this is 3.3.3 because it's router 3. So then we go to area 0 and advertise the network 10.0.23.0. Then the wildcard mask, like that. Okay. So now let's go ahead and check the next instruction on the lab guide. So OSPF LSDB. So remember, anytime you create different processes, you're going to have different LSDBs for each process, links to the database. So OSPF LSDB are significant only to the local router. So therefore, allowing routes from OSPF LSDB2 over 1 and at 3 to reach OSPF LSDB1 of R2. So let's run the command display interface that to verify the configuration that we've done so far. So we just want to display the details of that particular interface. Of that particular tunnel that we've created. So display int tunnel 001. So some of the details you can see is the physical state and the line protocol state of that particular tunnel, they are actually up. The other thing we can see is the internet address. So the internet address is that address that we've assigned to that tunnel on this router. But we have the tunnel source address, which is the address on the physical interface, gigabit Ethernet 0/0/1. Then we have the destination, the tunnel destination address, which is the physical address on the other end, on the branch router. At this point, we can also see that for this particular tunnel, keepalive has been disabled. So we can do the same on R3. So display interface tunnel 0/0/1. So here we can also see the physical status and the protocol, line protocol status is up. We can confirm the internet address we've given it, 100.1.1.2. We can also see the source, the tunnel source address, which is the address of the physical interface. This one here, G002, that is connecting R3 to the internet. And the destination is the physical address on the ingress interface of the headquarter router. Okay, so we can also see the tunnel protocol. Remember, we specified the tunnel protocol as GRE. So that's the other thing that I had not mentioned. So we can actually verify that indeed the tunnel protocol for this particular tunnel is GRE. Okay, so let's look at the next instructions here. So step number 4, verify that the routes are being carried via GRE. So we run the display IP routing table to check the IPv4 routing table. So let's go ahead on R1. So we just want to confirm whether we are going to see the routes that are on the branch, these loopback networks. So we can do display IP routing table. We can even specify the protocol because we've used OSPF. So we just want to see routes from OSPF. So indeed, we can see from R1 this particular route from the branch has been advertised. And also this route has also been advertised. They have been advertised. And if you can see, look at the interface. Look at the interface. So other than the next hop, it shows the interface. That is, if you want to go to this network, then you have to go through the tunnel on this router, tunnel 0/0/1. So this is the outgoing interface. So this packet is going to be forwarded through this tunnel if you're going to this network on the branch. So they're passing through the tunnel. That is the outgoing tunnel. And you can also see that the next hop is actually the address of the tunnel at the other end, at the branch. So that's the next hop address, 100.1.1.2. So it's not the address on the physical interface on the at the branch, but actually the address that we've configured for the tunnel at the end of the tunnel there. So it's important for us to note such details. We can also do so on R3 to confirm display IP routing table. We specify the protocol as OSPF so that we don't see everything. So on the branch, we can also see that networks from the headquarters have also been advertised here. So we have the 1.1, which is the loopback 0 network on R1, and we also have 10.11.11, this one. And as you can see, also from R3 will place any packets that are destined to this network. They'll have to go through the tunnel. And the next hop is the IP address of the tunnel at the headquarters end. Okay, so let's check what's next. So after a GRE tunnel is set up, the router can exchange OSPF packets through the GRE tunnel. So now we want to clear the IPsec statistics and test the connection. So you remember the IPsec statistics that was showing us how many packets have passed through the tunnel. So we just want to reset it. Then we do a ping from R1 loopback interface to R3 loopback interface. Then we can display the statistics and see whether really they go through, those packets will go through the GRE tunnel. So let's do the reset. Let's do the reset IPsec statistics ESP. Oh, I think we have to be on user view. So reset IPsec statistics. Then we can do a ping -A in order to specify the source. So the source is 1.1, which is on R1. The destination, we want it to go to 3.3, which is the loopback interface here on R3. So if we do the ping, it should be successful because we have that network in our routing table. And now we can do display IPsec statistics ESP. And we should actually see the number of packets that have passed through this particular tunnel. Let's just clear it first. Reset, then we display. So if we display after resetting 00, then after we do the ping, so we do the ping, and now if we do display, we should be able to see the packets that have passed through the tunnel. So incoming and outgoing packets, 77. Okay, so let's go ahead and check the next step here. So GRE encapsulates all OSPF traffic, including the hello packets over IPsec. So that's why even though we've sent only 5 ping requests, the numbers are differing because within that time, we are also sending OSPF hello packets through the GRE tunnel. So the gradual increment of the IPsec ESP statistics verifies this. So we know that OSPF sends hello packets after every 2 seconds. So that's why we are seeing that the number here will differ. So will differ from the total number of ping requests that we send. So here there are 7 because 2 of the packets are actually hello packets. So if I do the same command, display IP statistics, you can see now that we have more packets that have been sent, which are actually the OSPF hello packets. So that explains why the numbers there are differing. Okay. So now we implement the keep alive feature on the GRE tunnel. Keep alive is used to maintain the tunnel status and also to detect if one side of the tunnel is down in order to avoid what we call a black hole. Packets being sent over the tunnel, but the other end of the tunnel is actually down. So packets are going to be lost. So how do we enable the keep alive feature? Remember, you only need to enable keep alive on one end. So once you enable the keep alive on one end, after every 5 seconds by default, the router in which you've enabled the keep alive will be sending keep alive messages after every 5 seconds by default. That is what we call the period. So sometimes we might want to reduce from the default to a lower value. So right now we want to enable the keep alive on this particular tunnel to be sent after every 3 seconds. So that's what we call the period. The period. So let's go ahead and do exactly that on R1. So you don't have to configure keep alive on both R1 and R3, on only one side. So we go to system view, then we go into the tunnel, so tunnel 001, then keep alive. Let me do a question mark so that you see. So we have the period. Set the keep alive period parameter. So we can do period, then let me do a question mark. So it can be an integer between this, but the default is 5 seconds. So now we want to specify this as 3. So when we do 3, it means keep alive messages between these two routers. R1 is going to be sending keep alive messages after every 3 seconds. After every 3 seconds. Okay. So the other important parameter on keep alive is what we call the retry times. I don't know if they show it here. They don't. But the retry times is the number of times that. So anytime R1 sends a keep alive message, R3 should reply. Otherwise, if R3 does not reply, R1 will continue counting the number of keep alives that it has sent without receiving a reply. So if it gets to a maximum of 3 by default, so if R1 retries for 3 times without getting a reply from R3, then it will simply tear down the tunnel. It will simply tear down the tunnel in order to avoid the black hole issue. So that is what we call the keep alive retry. I don't know if, let me try keep alive. It's like it's not enabled on this particular, it's not enabled here. Let me see, period is there. So for example, 3, can we do retry? Good. So retry times, let me do a question mark. So retry times is the number of keep alive retries. So default is 3, and as I've explained, if R1 sends 3 retries, keep alive messages, without getting a response from R3, then it's going to tear down the tunnel. So the default retry times is 3. So maybe we can change that to 2 if we want to, just like that. So thank you very much for your patience, ladies and gentlemen. That is the end of this particular lab. I hope it has helped reinforce your understanding of the principles that we learned during the theory class. Does anyone have a question or a comment? Okay, sawa sawa. Asanteni sana.